Imagine looking up at the night sky and realizing that half of all the ordinary matter in the universe, the stuff that makes up stars, planets, and even you, has simply vanished without a trace. That's the baffling reality scientists have been grappling with for decades. We know it's out there somewhere, but where? This isn't some sci-fi mystery. It's one of the biggest unsolved puzzles in modern astrophysics, the missing baryon problem. Baryons, the particles that form the building blocks of everything we can see and touch, seem to have disappeared from the cosmic ledger, leaving researchers scratching their heads. And yet, hidden in the vast expanse of space, there are clues, 25 of them, that might finally crack this celestial cold case wide open. Think about that for a second. Nearly half of all the normal matter in the universe is unaccounted for. It's not dark matter, not some exotic substance. It's the same protons and neutrons that make up galaxies, planets, and even your morning coffee. So where did it all go? The answer lies in the delicate dance of cosmic structures, the faint whispers of intergalactic gas, and the invisible threads that weave the universe together. Scientists have spent years piecing together this puzzle, tracing faint signals across billions of light years, and what they've uncovered is nothing short of extraordinary. From the filaments of the cosmic web to the scorching plasma between galaxies, the missing baryons are hiding in plain sight, if you know where to look. This isn't just a story about numbers or abstract physics. It's a tale of human curiosity and relentless exploration. Every clue brings us closer to understanding not just where the missing matter is, but how the universe itself operates on the grandest scales. What started as a frustrating gap in our cosmic accounting has blossomed into one of the most thrilling detective stories in astronomy, and the best part: you don't need a telescope to join the hunt. Over the course of this journey, we'll unravel each of those 25 clues, revealing how scientists are closing in on the answer, and why solving this mystery could rewrite our understanding of the cosmos. So buckle up, the universe has been hiding something, and we're about to find it. The first clue takes us into the sprawling architecture of the universe itself, the cosmic web. Picture an unimaginably vast network of threads stretching across billions of light years, connecting galaxies like beads on a string. These filaments, made mostly of hydrogen gas, are where theorists believe a huge fraction of the missing baryons could be hiding. It's not that they're gone, they're just incredibly hard to see. Why? Because this matter isn't clumped together in neat, glowing clouds like stars or galaxies. Instead, it's spread out in such thin, diffuse strands that it barely emits any light at all. For decades, supercomputer simulations have predicted that these filaments should contain enough gas to account for a significant portion of the missing baryons. The math checks out, but when astronomers point their telescopes at these regions, they often come up frustratingly empty-handed. The problem isn't the theory, it's the signal. The gas in these filaments is so hot and so sparse that it emits only the faintest traces of X-rays or ultraviolet light, making it nearly invisible to conventional telescopes. That hasn't stopped scientists from trying. Some of the most advanced space telescopes, like the Chandra X-ray Observatory and the European Space Agency's XMM Newton, have spent years scanning the sky for these elusive signals. Occasionally, they catch a glimpse, a slight distortion in the light of distant quasars, or a faint X-ray glow from the space between galaxy clusters. These fleeting detections are like finding footprints in the dark, proof that something massive passed through, even if we can't see it directly. But here's where things get even more intriguing. The gas in these filaments isn't just sitting still, it's moving, flowing, and even colliding in ways that might leave subtle marks on the cosmic background radiation, the faint afterglow of the Big Bang. Some researchers are now turning to next-generation telescopes, like the upcoming Athena mission, to hunt for these whispers in the dark. If they succeed, it could finally confirm what simulations have long suggested: that the cosmic web isn't just scaffolding for galaxies, it's a reservoir for the universe's missing matter. This isn't just about filling in a gap in our cosmic inventory. If these filaments really do hold the missing baryons, it would mean that the universe's structure is even more finely balanced than we thought, threaded with invisible rivers of matter that shape everything from the birth of galaxies to the fate of the cosmos itself. And that's just the first clue. While the cosmic web presents one promising hiding spot for the missing baryons, there's another shadowy realm where they might be lurking, a place so diffuse and scorching hot that it's practically invisible. Scientists call it the warm-hot intergalactic medium, or WHIM for short. Picture this, an ocean of superheated gas stretching between galaxies, so thin you could fly a spaceship through it for millions of years without hitting a single atom, yet collectively, it might hold enough matter to solve half the mystery. This isn't just any gas. The WHIM is a ghostly plasma, heated to temperatures between 100,000 and 10 million degrees, stripped down to its barest atomic components by the sheer violence of cosmic evolution. It's the aftermath of the universe's turbulent adolescence, when galaxies formed, collided, and flung matter into the void with unimaginable force. But detecting this material is like trying to spot steam rising from a cup of coffee in a thunderstorm. It's there, but nearly impossible to isolate. That's where X-ray and ultraviolet telescopes come in. When light from distant quasars, the brilliant cores of ancient galaxies, passes through these invisible tendrils of gas, some of it gets absorbed. The WHIM doesn't glow brightly on its own, but it leaves fingerprints on the light that travels through it, like a cosmic dye test. Telescopes like NASA, Chandra, and Hubble have spent years analyzing these subtle imprints, hunting for the telltale signatures of oxygen and other heavy elements that were forged in stars and then blasted into intergalactic space. Occasionally, they get lucky. In 2018, researchers using Hubble data spotted the absorption lines of highly ionized oxygen in the light of a quasar several billion light-years away. It was a whisper, but a crucial one, direct evidence that the WHIM exists and could be hoarding a significant chunk of the missing baryons. Still, these detections are rare, like finding a needle in a haystack the size of a galaxy cluster. The challenge isn't just spotting the WHIM, it's mapping it. Unlike galaxies or stars, this stuff doesn't stay put. It's caught in a dynamic dance, funneled by gravity into vast cosmic currents, shock heated by colliding galaxy clusters, and constantly shifting shape. Some simulations suggest up to half the missing baryons could be hiding here, woven into the fabric of space itself, just too sparse and too hot for our current tools to see clearly. New missions are on the horizon to change that. The upcoming European Space Agency's Athena telescope, set to launch in the 2030s, will carry instruments sensitive enough to map the WHIM in unprecedented detail. Imagine peeling back an invisible layer of the universe, revealing the hidden rivers of matter that have eluded us for decades. If these observations pan out, they could confirm that the WHIM isn't just a theoretical curiosity, it's the universe's way of balancing the books. What makes this clue so compelling isn't just the science, it's the sheer audacity of the hunt. We're talking about particles so spread out that a single cubic meter of this gas might contain just one lonely atom, yet across billions of light-years, it adds up to something colossal. Solving this piece of the puzzle wouldn't just fill in a gap in our cosmic accounting. It would rewrite the story of how matter moves, evolves, and shapes the universe on the grandest scales. And we're just getting started. Galaxies aren't just serene islands of stars, they're cosmic engines, blasting matter into the void with unimaginable force. When a massive star explodes as a supernova, it doesn't just leave behind a remnant. It sends shockwaves rippling through its host galaxy, hurling vast amounts of gas outward at speeds of thousands of kilometers per second. These aren't gentle breezes, they're tempests powerful enough to reshape entire galaxies and fling baryons far beyond where telescopes can easily spot them. Active galactic nuclei, the furious cores of galaxies fueled by supermassive black holes, take this chaos to another level. As matter spirals toward the black hole, some of it gets funneled into jets and winds that erupt outward, carving through interstellar space like cosmic fire hoses. These outflows can stretch for millions of light years, carrying with them enough ordinary matter to tip the scales of the missing Baryon problem. The irony. The very processes that make galaxies shine, supernova, and black hole activity are also the ones scattering their building blocks into the darkness. Detecting this lost matter is like trying to trace smoke in a hurricane. The gas expelled by these outflows is ionized, meaning its atoms have been stripped of electrons, leaving it virtually invisible to optical telescopes. But it's not entirely undetectable. Astronomers look for subtle clues, faint X-ray emissions, distortions in the light of background quasars, or even the slight dimming of distant galaxies as their light passes through these diffuse clouds. Each observation is a breadcrumb, hinting at how much of the universe's missing matter might be hiding in plain sight, just spread so thin that it blends into the cosmic background. Some of the most compelling evidence comes from nearby starburst galaxies, where frenetic star formation drives relentless outflows. In places like Messier 82, telescopes have spotted vast plumes of gas streaming away from the galactic disk, enriched with heavy elements forged in stellar furnaces. These outflows don't just vanish, they join the intergalactic medium, becoming part of the WHIM or weaving into the cosmic web. Simulations suggest that over billions of years, as much as half a galaxy's baryons could be lost this way, ejected into the great beyond by the very stars and black holes that define it. Yet here's the twist, these outflows might not be a one-way trip. Some models predict that galactic winds could eventually stall, cool, and even rain back down onto their home galaxies in a process called recycling. It's a cosmic water cycle, but instead of rain, it's gas, scorching hot plasma that might one day fuel new generations of stars. If true, the missing baryons aren't truly missing. They're just on a detour, caught in an eons-long journey between galaxies and the voids between them. Unraveling this clue requires piecing together a puzzle that spans both space and time. It's not enough to spot outflows, we need to track where they go, how they mix with the intergalactic medium, and whether they ever return. New instruments like the James Webb Space Telescope are already probing these questions, peering into the hearts of distant galaxies to measure their winds with unprecedented precision. Meanwhile, upcoming X-ray observatories promise to map the hot gas halos around galaxies, tracing the invisible highways along which baryons travel. What makes this clue so fascinating isn't just the science, it's the narrative. Galaxies aren't static. They breathe, they erupt, they lose pieces of themselves and sometimes reclaim them. The missing baryons might not be a flaw in our cosmic accounting, but a testament to the dynamic, ever-changing nature of the universe itself. And if we can learn to read these galactic winds like cosmic weather patterns, we might finally solve one of astronomy's most persistent mysteries. Dark matter may be invisible, but its fingerprints are everywhere, especially when it comes to the missing baryon problem. Picture a galaxy like our Milky Way, not as a lone island of stars, but as the glowing center of something far more massive. A vast, invisible cocoon of dark matter stretching hundreds of thousands of light years into space. These halos, as astronomers call them, don't just sit there. They shape the destiny of ordinary matter through sheer gravitational force. And if we're searching for where the universe stashed its missing baryons, these ghostly structures might hold the key. Here's how it works. When dark matter halos form in the early universe, their immense gravity acts like a cosmic net, pulling in surrounding gas, the same gas that should eventually become stars, planets, and everything we see. But not all of it makes it to the center. Some gets trapped in the halo's outer reaches, heated to extreme temperatures by shock waves from collapsing gas or collisions with other halos. This creates vast, diffuse reservoirs of ionized gas, too hot to form stars, too faint to detect easily, but massive enough to account for a significant chunk of the missing baryons. The challenge is catching these hidden reservoirs in the act. Unlike a glowing nebula or a blazing star, this gas doesn't emit much light. It's spread out across such enormous volumes that even the most sensitive telescopes struggle to spot it. But astronomers have tricks up their sleeves. One method involves looking for subtle distortions in the cosmic microwave background, the afterglow of the Big Bang. As this ancient light passes through hot gas in dark matter halos, some of its photons get a tiny energy boost, leaving a faint imprint that specialized instruments like the Atacama Cosmology Telescope can detect. Another clue comes from gravitational lensing, the way dark matter bends light from distant galaxies. By studying these distortions, scientists can map the distribution of mass in halos, revealing where ordinary matter might be hiding. Sometimes the math doesn't add up. There's more gravity than visible matter can explain, hinting at enormous envelopes of hot gas surrounding galaxies like a steamy, invisible shroud. But dark matter halos don't just hide baryons, they might also redistribute them in unexpected ways. Simulations show that when halos collide, the resulting turbulence can slosh trapped gas around like water in a spinning bucket, ejecting some of it entirely into intergalactic space. This could explain why galaxy clusters often seem underweight in ordinary matter. Their baryons aren't gone. They've just been flung into the cosmic equivalent of the backseat where they're harder to spot. The implications go beyond bookkeeping. If dark matter halos are hoarding baryons, it means the universe's structure is even more interconnected than we thought. The same invisible scaffolding that holds galaxies together is also quietly dictating where ordinary matter ends up and how much of it stays visible to us. New telescopes like the Vera C. Rubin Observatory aim to probe these halos in unprecedented detail, peeling back the layers of this cosmic hide and seek. What's remarkable isn't just the scale of this hidden reservoir, it's the elegance of the solution. Dark matter, long considered the universe's silent partner, might finally be revealing its role in one of astronomy's greatest puzzles. The missing baryons could be closer than we think, woven into the very fabric of the halos that shape the cosmos. And if we're right, it's proof that even the darkest corners of the universe play by the same rules. We just have to learn how to read them. Galaxy clusters should be baryon treasure chests, dense cities of stars, gas, and dark matter where ordinary matter piles up in staggering amounts. Yet when astronomers tally the numbers, something's off. These colossal structures, some containing thousands of galaxies, seem to hold only about half the baryons predicted by cosmic calculations, the rest. Another piece of the missing matter puzzle, hiding in plain sight within the very places we thought we knew best. At the heart of this mystery lies the intracluster medium, a seething ocean of superheated gas that fills the spaces between galaxies in a cluster. This isn't just any gas, it's plasma, ionized to temperatures of tens of millions of degrees, glowing faintly in X-rays like a cosmic ghost light. For decades, scientists assumed this fiery soup accounted for most of a cluster's baryons. But detailed observations reveal a gap. Even with this scorching reservoir, the numbers still don't add up. Where's the rest? One answer might lie in the outskirts of these clusters, where gas is cooler and far harder to detect. Imagine a bustling metropolis where the downtown core is easy to map, but the suburbs stretch into near invisibility. Telescopes like Chandra and XMM Newton have spotted hints of this elusive matter. Filaments of warm gas lacing the outer edges of clusters, too diffused to emit strong X-rays but massive enough to tip the scales. These faint structures could be the universe's way of stashing baryons where we least expect them, just beyond the glow of the cluster's bright center. Then there's the role of turbulence. Galaxy clusters aren't serene, they're cosmic battlegrounds, where galaxies collide, merge, and send shockwaves rippling through the intracluster medium. This chaos doesn't just heat the gas, it can fling it outward, redistributing baryons into regions so vast and tenuous they evade detection. Some simulations suggest up to 30% of a cluster's baryons might be hiding in these turbulent outskirts like foam scattered by a crashing wave. But the plot thickens when we consider dark matter's role. Clusters sit at the intersections of the cosmic web, where dark matter's gravity funnels gas into these dense knots. Yet that same gravity might also be pushing baryons away. During cluster collisions like the famous bullet cluster, dark matter and gas can become separated, leaving pockets of ordinary matter stranded in the cosmic equivalent of no man's land. These lost baryons aren't truly missing, they've just been shuffled out of view by the universe's invisible hand. What's fascinating isn't just the hiding spots, it's the implications. If clusters are missing baryons, it challenges our understanding of how these structures form and evolve. Did some gas get expelled during the cluster's violent youth? Or is it cooling and condensing into unseen clouds too faint to spot? The answer might lie in next-generation telescopes like Athena, which could map the full extent of cluster gas from its blazing core to its shadowy fringes. This clue reminds us that even the most studied corners of the universe still hold secrets. Galaxy clusters, once thought to be cosmic ledger keepers, might actually be accomplices in the great Baryon disappearance. And as we piece together their hidden ledgers, we're not just solving a mystery, we're rewriting the story of how the universe structures itself on the grandest scales. Sometimes the universe leaves its fingerprints in the quietest places, like the faint afterglow of the Big Bang itself. The cosmic microwave background, that ancient light frozen in time, holds secrets we're only just learning to read. One of those secrets is the Sunyaev-Zeldovich effect, a subtle distortion in this primordial radiation that acts like a cosmic X-ray, revealing hidden pockets of matter we'd otherwise never see. Here's how it works. When the universe was just 380,000 years old, it released a burst of light as atoms first formed, a flash now stretched into microwaves that permeate all of space. But as this light travels toward us, it doesn't always arrive untouched. If it passes through a galaxy cluster or a filament of the cosmic web, the hot electrons in that gas give the photons a tiny energy boost. It's like rolling a marble through a field of pebbles. Each little collision kicks it slightly harder, leaving a telltale signature in the light spectrum. What makes this effect so powerful is its sensitivity to even the most diffuse gas. Unlike X-ray telescopes, which struggle to detect faint, spread-out plasma, the Sunyaev-Zeldovich signal doesn't fade with distance. That means it can spot baryons hiding in the vast outskirts of galaxy clusters or tangled in the cosmic web's faintest threads, precisely where theorists suspect the missing matter might be lurking. Recent observations have turned this from theory into reality. The Atacama Cosmology Telescope and the Planck satellite have mapped these distortions across huge swaths of sky, uncovering hints of gas where traditional telescopes see nothing. In 2021, researchers using data from the South Pole Telescope even detected the Sunyaev-Zeldovich signal in the warm, hot intergalactic medium, the first direct evidence that this elusive plasma might hold a significant stash of the universe's missing baryons. But the real breakthrough came when astronomers combined these observations with other techniques. By cross-referencing Sunyaev-Zeldovich maps with gravitational lensing data, they've begun to weigh invisible gas clouds indirectly, like measuring the depth of a pond by watching how ripples bend around submerged rocks. The results are startling. Some galaxy clusters appear to have up to twice as much ordinary matter as their X-ray emissions suggest, with the excess hiding in those hard-to-see outer regions. The implications go beyond solving a cosmic accounting error. If the Sunyaev-Zeldovich effect is revealing baryons where we least expected them, it means our understanding of how matter clusters in the universe is fundamentally incomplete. Gas isn't just pooling in the brightest, hottest centers of galaxy clusters, it's spreading into the shadows, tracing a hidden architecture we're only now beginning to map. New instruments are pushing this frontier even further. The upcoming Simons Observatory in Chile will scan the sky with unprecedented precision, while future space missions aim to resolve these distortions in finer detail than ever before. Each observation is a step toward reconciling the universe's ledger, proving that even the oldest light in the cosmos still has stories to tell, and in those whispers from the dawn of time, we might finally find the missing pieces of our cosmic puzzle. Fast radio bursts are cosmic enigmas, brief, intense blasts of radio waves that flash across the universe in milliseconds, then vanish without warning. But for astronomers hunting missing baryons, these mysterious signals aren't just curiosities. They're celestial flashlights illuminating the dark corners of the cosmos. Here's why: as an FRB travels billions of light years to reach us, it doesn't move through empty space. It cuts through clouds of ionized gas, filaments of the cosmic web, and halos of dark matter, each encounter leaving a tiny but measurable mark on the signal. The key lies in something called dispersion, the way these bursts get stretched out like a cosmic accordion as they traverse the universe. Denser regions slow down the lower frequency components of the burst more than the higher ones, creating a delay that scientists can measure down to the nanosecond. By calculating how much a burst has dispersed, researchers can work backward to map the total number of electrons, and by extension, the baryons it encountered along its path. It's like listening to an echo in a cavern and deducing not just the distance to the walls, but the density of the air between them. Some of the most exciting discoveries have come from localized FRBs, those traced back to specific galaxies. In 2020, astronomers studying a burst from a distant spiral galaxy found far more dispersion than expected, suggesting it had passed through a massive, previously invisible reservoir of ionized gas. This wasn't just a wispy filament, it was a baryon motherlode potentially holding enough matter to account for a significant fraction of the universe's missing mass. But FRBs don't just reveal where baryons are, they expose where they aren't. When bursts pass through seemingly empty voids between galaxy clusters and show minimal dispersion, it hints that these regions truly are as barren as they appear, ruling out some theories about hidden matter lurking in the cosmic deserts. Other bursts have traced the outlines of the warm, hot intergalactic medium, their dispersion measures aligning eerily well with simulations of that elusive plasma. The real power of FRBs lies in their randomness. Unlike quasars or galaxies, which cluster along certain lines of sight, these bursts come from all corners of the sky, sampling the universe's matter distribution in a way no other tool can. Future telescopes like the Square Kilometre Array will detect thousands of FRBs annually, transforming them into a vast network of cosmic probes. Each burst is a snapshot, a single frame in a grand mosaic of the universe's hidden structure. What makes this clue so revolutionary isn't just the science, it's the serendipity. These bursts, once dismissed as astrophysical oddities, have become one of our sharpest tools for mapping the invisible. They're proving that the missing baryons aren't lost, they're just waiting for the right light to shine on them. And as each new burst cracks the cosmic vault a little wider, we're reminded that sometimes the universe's greatest secrets reveal themselves in the blink of an eye. Quasars are the universe's lighthouses, beacons so bright they can be seen from billions of light years away. But their brilliance isn't just for show. As their light travels across the cosmos, it passes through clouds of gas, each one leaving behind a unique fingerprint in the quasar's spectrum. These absorption lines, as astronomers call them, are like cosmic barcodes, revealing the composition, temperature, and density of the invisible matter strewn between galaxies. And hidden in these subtle patterns could be the answers to where the missing baryons have gone. The magic lies in the details. When quasar light encounters a cloud of gas, specific wavelengths get absorbed by atoms within that cloud. For example, hydrogen, the most abundant element in the universe, leaves a distinct mark at a wavelength of 121.6 nanometers. By analyzing how these lines appear, whether they're sharp or smeared, strong or faint, scientists can reconstruct the gas's location, motion, and even its role in the cosmic web. Some of the most revealing discoveries have come from the Lyman alpha forest, a dense thicket of absorption lines caused by countless hydrogen clouds along the quasar's path. It's like reading the rings of a tree, but instead of years, each line tells the story of a different filament or knot in the universe's vast structure. But this method isn't without its challenges. The warmer and more ionized the gas, the fainter its absorption lines become, making it incredibly difficult to detect the very reservoirs, like the warm, hot intergalactic medium where theorists suspect most missing baryons are hiding. It's the equivalent of trying to spot a whisper in a hurricane. That's where heavy elements like oxygen and carbon come in. Even trace amounts of these elements, forged in stars and blasted into intergalactic space, can leave clearer absorption signatures in a quasar spectrum. In 2015, researchers using the Hubble Space Telescope spotted these metals in the WHIM for the first time, confirming that at least some of the missing baryons were lurking in these ultra-diffuse clouds. Yet for all its power, the quasar absorption line technique has blind spots. Since it relies on background light sources, it only probes matter along narrow, pencil-thin beams through the universe, like trying to map a foggy landscape with a single laser pointer. And with quasars being rare and unevenly distributed, vast swaths of the cosmos remain uncharted. New instruments like the James Webb Space Telescope and the upcoming Extremely Large Telescope promise to expand this map, peering deeper into the infrared where distant quasars shine brightest and uncovering fainter absorption lines than ever before. What makes this clue so compelling isn't just the science, it's the poetry. Every quasar spectrum is a message bottled in light, carrying echoes of the gas it passed through on its journey to us. And as we learn to decode these cosmic hieroglyphs, we're not just solving a puzzle, we're reconstructing the unseen architecture of the universe itself, one absorption line at a time. Counting atoms across the cosmos might sound straightforward until you realize the universe doesn't keep receipts. The Baryon census problem is like trying to balance a bank account where half the transactions are written in invisible ink. Cosmologists have precise predictions for how much ordinary matter should exist based on the cosmic microwave background, about 4.6% of the universe's total content. Yet when astronomers tally up all the visible stars, galaxies, and gas clouds, they come up startlingly short, missing nearly half the expected baryons. So where's the discrepancy? Part of the challenge lies in the sheer scale of the hunt. Imagine searching for water in a desert by examining every grain of sand individually. That's what detecting diffuse baryons feels like. Theoretical models honed by supercomputer simulations paint a clear picture. Baryons should be distributed among galaxies, galaxy clusters, and the vast intergalactic medium in specific ratios. But observations tell a different story. Take galaxy clusters, for example. These massive structures, bound together by gravity, should act as baryon storehouses. Yet even they only account for about half the expected matter within their boundaries. The rest appears to have leaked out into the surrounding cosmic web, or perhaps evaporated into the warm, hot intergalactic medium where traditional telescopes struggle to spot them. The gaps grow even wider when we zoom out to the universe's large-scale structure. Simulations predict that roughly 40% of baryons should reside in the cosmic web's filaments, those sprawling threads of gas connecting galaxy clusters. But observations of these regions using tools like quasar absorption lines or the Sunyaev-Zeldovich effect have only recovered a fraction of that predicted mass. It's as if the universe has a habit of stashing its matter in the hardest places to look. Then there's the temperature problem. Baryons aren't just spread thin, they're often too hot or too cold to detect easily. The warm-hot intergalactic medium, with its million-degree plasma, emits faint X-rays that blur into the cosmic background, while cooler gas in cosmic voids absorbs light at wavelengths our telescopes aren't always optimized to see. This creates observational blind spots, like trying to take a census where entire populations are invisible to the naked eye. Even the tools we use introduce uncertainties. Quasar absorption lines, for instance, only sample narrow lines of sight, leaving vast regions unexplored. Fast radio bursts provide broader coverage but are still too rare to map the universe comprehensively. And while X-ray telescopes like Chandra excel at spotting hot gas in galaxy clusters, they're less sensitive to the fainter emissions from the cosmic web's outermost tendrils. The solution isn't just better instruments, it's smarter accounting. Some researchers are now combining multiple detection methods, cross-referencing data from X-ray, ultraviolet, and radio observations to fill in the gaps. Others are revisiting theoretical models, questioning whether assumptions about baryon clustering or feedback processes need tweaking. The answer might not lie in one grand discovery, but in countless small corrections, each shaving away at the discrepancy until the cosmic ledger finally balances. What makes this clue so humbling is its reminder of how much we still don't know. The missing baryon problem isn't just a puzzle, it's a test of our ability to see the universe clearly, to measure what's hidden in plain sight. And with every new observation, we're not just closing a gap in our calculations, we're learning how to read the universe's fine print. About 13 billion years ago, the universe went through a dramatic transformation, one that might hold the key to today's missing baryon mystery. Picture the cosmos in its infancy, a fog of neutral hydrogen so thick that light couldn't travel far without scattering. Then something changed. The first stars and galaxies flickered to life, their intense radiation stripping electrons from atoms in a process called reionization. This cosmic dawn didn't just illuminate the universe, it fundamentally reshaped where baryons could hide. The connection to our modern missing matter problem lies in the chaos of that era. As reionization swept across the cosmos, it didn't just light up the gas, it superheated it, turning calm hydrogen clouds into turbulent plasma. Some simulations suggest this could have blasted baryons clear out of galaxies and into the intergalactic void, where they remain today as part of the warm, hot intergalactic medium. Think of it like a cosmic game of pool. The energy from those first stars acted as the cue ball, scattering matter into corners of the universe we're still struggling to observe. But reionization impact might go even deeper. During this period, the universe's structure was still forming, meaning the distribution of matter was far more malleable. Gas that might have otherwise collapsed into galaxies could have been pushed away by the pressure of ionizing radiation, creating vast bubbles of ionized hydrogen around early stellar nurseries. Over billions of years, these bubbles expanded and merged, potentially trapping baryons in diffuse reservoirs between galaxies, the same reservoirs that now elude our telescopes. The challenge is proving this hypothesis. Reionization ended over 12 billion years ago, and its fingerprints are faint. Yet astronomers have found clever ways to investigate. By studying the most distant quasars whose light was emitted during or just after reionization, researchers can analyze absorption lines to map how gas was distributed back then. Surprisingly, these observations show patches of both neutral and ionized hydrogen coexisting, suggesting reionization wasn't a uniform process but a messy, uneven one. This patchiness could explain why some baryons ended up in hard-to-detect regions. They were swept up in cosmic tides during this turbulent chapter. New tools are bringing this era into sharper focus. The James Webb Space Telescope is peering back to when the first galaxies formed, revealing how their radiation shaped surrounding gas. Meanwhile, radio telescopes like the Square Kilometre Array Precursor projects aim to detect the faint glow of neutral hydrogen from the reionization epoch itself. If these observations confirm that baryons were systematically displaced during this cosmic upheaval, it would mean the missing matter isn't lost. It's just been drifting in intergalactic space since the universe's formative years. What's fascinating isn't just the potential solution, it's the timescale. The same violent starbirth that lit up the early universe may have inadvertently hidden half its matter from our view. Solving this clue wouldn't just fill a gap in our cosmic accounting, it would show how events from the dawn of time continue to shape the universe we see today. Dwarf galaxies should be cosmic underdogs, tiny, fragile systems where every atom counts. Yet when astronomers inventory their matter, they find something puzzling. These galaxies often hold far fewer baryons than predicted by cosmological models. It's as if the universe handed them a starter kit of ordinary matter, only for half of it to vanish into thin space. But the truth is far more dramatic. Dwarf galaxies aren't just missing baryons, they've been robbed repeatedly by the harsh realities of cosmic evolution. Take tidal stripping, for example. Imagine a dwarf galaxy orbiting a much larger neighbor like the Milky Way. With each pass, the bigger galaxy's gravity tugs at the smaller one, peeling away its outermost gas and stars like layers of an onion. Over billions of years, this slow-motion theft can strip a dwarf galaxy of most of its baryonic matter, leaving behind a ghostly core of stars and dark matter. The evidence is written in the cosmos. Dwarf spheroidal galaxies, which orbit close to giants like Andromeda or our own Milky Way, are notoriously baryon-poor compared to their isolated cousins. Their missing matter isn't lost, it's been siphoned off into the vast halos of their massive neighbors, where it blends into the intergalactic background. But gravity isn't the only culprit. Feedback mechanisms, the violent processes triggered by star formation and supernova, can also blow baryons straight out of dwarf galaxies. These tiny systems have shallow gravitational wells, meaning even a single supernova explosion can heat and eject gas with astonishing efficiency. Picture a souffle collapsing under its own weight. When stars erupt in a dwarf galaxy, the resulting shockwaves can puff its gas into space like cosmic steam, leaving behind a baryon-depleted husk. Some simulations suggest that up to 90% of a dwarf's original gas could be lost this way, expelled into the void before it ever forms new stars. Then there's reionization's lingering shadow. During the universe's early years, the intense ultraviolet radiation from the first galaxies may have prevented dwarf galaxies from ever collecting their fair share of baryons in the first place. Small systems forming during this era would have had their gas ionized and heated, making it too energetic to collapse into stars. It's like trying to fill a bucket with holes. The moment these galaxies started gathering matter, the universe tore it away, leaving them permanently stunted. Yet the story isn't entirely bleak. Some dwarf galaxies, particularly those in quiet cosmic backwaters, have held onto their baryons against the odds. These gas-rich dwarfs, like the famous Leo T or Aquarius systems, are cosmic time capsules offering glimpses of what small galaxies might look like if left undisturbed. Studying them alongside their baryon-starved relatives helps astronomers piece together the full narrative, not just of where the missing matter went, but how the universe's smallest galaxies fight to survive in a cosmos stacked against them. What makes this clue so compelling isn't just the mystery, it's the scale of the forces at play. Dwarf galaxies remind us that the universe isn't a static gallery of objects but a dynamic battlefield, where gravity, radiation, and sheer cosmic violence constantly reshape the distribution of matter. And as we uncover their secrets, we're not just solving a puzzle, we're learning how the universe treats its smallest inhabitants. Magnetic fields weave through the cosmos like invisible threads, shaping everything from star formation to galactic winds. But could these unseen forces also be hiding some of the universe's missing baryons? The idea isn't as far-fetched as it sounds. Picture a spiderweb catching droplets of water. Similarly, magnetic fields might trap and confine ionized gas in intergalactic space, keeping it just out of reach of our telescopes. These fields don't just nudge particles around, they can fundamentally alter how matter behaves. In regions where magnetic forces are strong, charged particles spiral along field lines like beads on a wire, making it harder for gas to clump together or emit detectable radiation. This could explain why some baryons remain invisible. They're not absent, just locked into diffuse, magnetized structures that evade traditional observation methods. Galaxy clusters offer a glimpse of this phenomenon. Their intracluster medium is threaded with magnetic fields strong enough to influence the motion of hot gas, potentially preventing it from cooling and forming stars, or from revealing itself clearly in our instruments. But the real intrigue lies in the cosmic web's filaments. Simulations suggest that weak magnetic fields, amplified over billions of years by turbulent gas flows, could create vast magnetic halos around these tendrils of matter. If true, these fields might stabilize otherwise fragile gas clouds, preventing them from dissipating or collapsing, effectively preserving baryons in a state that's diffuse enough to avoid detection, yet dense enough to account for the missing mass. The challenge, measuring fields this faint, is like trying to sense a whisper in a windstorm. There's another twist. Magnetic fields could be masking baryons not just by confining them, but by scrambling the signals we rely on to find them. When light from distant quasars passes through magnetized gas, its polarization, the orientation of its light waves, can subtly shift. Normally, this effect is minimal, but in regions where fields are tangled and strong, the distortion might blur absorption lines just enough to make ionized gas clouds appear fainter than they really are. It's the cosmic equivalent of a hall of mirrors, where the very tool meant to reveal hidden matter ends up obscuring it instead. Recent observations hint that this could be more than theoretical. Astronomers studying the radio emission from galaxy clusters have detected faint, large-scale magnetic fields extending far beyond the visible gas. Meanwhile, studies of polarized light from the cosmic microwave background suggest that primordial magnetic fields dating back to the universe's infancy might still linger in intergalactic space. If these relics are strong enough to influence gas dynamics today, they could be the missing piece in our baryon accounting, not by removing matter, but by rearranging it into forms we're still learning to see. Unraveling this clue will require more than just better telescopes. It demands new ways of thinking about how matter and magnetism interact across cosmic scales. Upcoming radio observatories like the Square Kilometre Array aim to map these faint fields with unprecedented precision, while advanced simulations explore how they might reshape our understanding of cosmic structure. What's clear is that magnetic fields aren't just passive bystanders in the universe, they're active players, twisting the fabric of space to hide baryons in plain sight. And if we're right, cracking this magnetic code could finally close one of astrophysics' most stubborn gaps. Baryon acoustic oscillations may sound like complex physics jargon, but they're actually one of the most elegant fingerprints of the early universe, a cosmic echo that helps us trace where baryons should be. Rewind to just 380,000 years after the Big Bang. The universe was a seething plasma of particles so dense that light couldn't travel freely. But within this hot soup, something remarkable was happening. Sound waves, packets of compressed baryons and photons sloshed outward from regions of high density, like ripples spreading from a stone dropped in a pond. These waves traveled about 500,000 light-years before freezing in place as the universe cooled and atoms formed. What remained was a subtle pattern, a series of concentric shells where matter was slightly more or less dense than average. Fast forward billions of years, and that pattern should still be imprinted on the universe's large-scale structure, like fossilized ripples in the cosmic web. The beauty of baryon acoustic oscillations lies in their predictability. Because those early sound waves propagated at a known speed before stopping, they left a characteristic scale. a standard ruler in the cosmos that astronomers can use to measure distances and map matter distribution. When we look at galaxies today, we find they're slightly more likely to be separated by this key distance, approximately 500 million light-years, than by any other. It's as if the universe has a hidden grid, with galaxies preferentially clustering at the peaks of those ancient waves. But here's where it ties into the missing Baryon problem. If we compare observations of these oscillations with predictions from cosmic microwave background data, something doesn't quite match up. The galaxy surveys show the right spacing, proof that baryons were there during those early sound waves, but the total mass accounted for today falls short. This discrepancy hints that while baryons played their part in shaping the universe's structure, many later slipped into the shadows, evading our detection. The real power of baryon acoustic oscillations comes when combined with other tools. For instance, by cross-referencing these galaxy distribution maps with measurements of the Sunyaev-Zeldovich effect or quasar absorption lines, astronomers can triangulate where the missing baryons might be hiding. Some seem to lurk in the diffuse outskirts of galaxy clusters, while others may be entwined in the cosmic web's faintest filaments, too thinly spread to emit detectable light but still contributing to that primordial pattern. New galaxy surveys like the Dark Energy Spectroscopic Instrument are taking this hunt to the next level. By mapping millions of galaxies in unprecedented detail, they're sharpening our view of these oscillations and narrowing the gap between prediction and observation. The more precisely we measure these frozen ripples, the closer we get to pinpointing where the universe stashed its missing matter. What makes this clue so compelling is its duality. Baryon acoustic oscillations are both a relic of the universe's infancy and a modern-day forensic tool, bridging the gap between ancient physics and contemporary mysteries. They remind us that the cosmos has a memory, one that's still whispering secrets about where its lost matter might be. Galaxies don't float in empty space, they're cocooned in vast, swirling envelopes of gas that stretch hundreds of thousands of light-years into the void. This circumgalactic medium, a term that rolls off the tongue with far less drama than the reality it describes, is one of the most chaotic and least understood frontiers in modern astronomy. Think of it as a galaxy's atmospheric halo, except instead of pleasant weather, it's a turbulent soup of superheated plasma, shredded gas clouds, and cosmic debris, all of which might be hoarding a significant chunk of the universe's missing baryons. For decades, astronomers assumed these halos were mere afterthoughts, leftover scraps from galaxy formation too sparse to matter. But recent observations have flipped that view on its head. The circumgalactic medium isn't just a wispy fringe, it's a dynamic battleground where gas from dying stars, galactic winds, and even intergalactic material collides, mixes, and sometimes escapes entirely. Some simulations suggest that in massive galaxies like our Milky Way, as much as half of all baryons could be hiding right here, in this frenetic zone just beyond what our telescopes traditionally classify as the galaxy itself. Mapping this region is like trying to study a thunderstorm by only looking at the raindrops that hit your window. The gas is so hot it emits faint X-rays, so diffuse it barely absorbs light, and so complex that no single instrument can capture its full story. That's where innovative tools like the Keck Cosmic Web Imager and the Hubble Space Telescope's ultraviolet spectrographs come in. By analyzing the light of distant quasars as it passes through these halos, astronomers have spotted telltale absorption lines from oxygen, nitrogen, and carbon elements forged in stars and then hurled into the circumgalactic medium by supernova or black hole winds. Each detection is a breadcrumb, hinting at the sheer volume of matter hiding in plain sight. But the real breakthroughs are coming from a new generation of telescopes designed specifically to probe these elusive halos. The upcoming James Webb Space Telescope, with its unparalleled infrared sensitivity, will peer through dust clouds that veil parts of the circumgalactic medium, while the European Space Agency's Athena mission will map its hottest, most energetic regions in X-rays. Even ground-based observatories like the Extremely Large Telescope, set to begin operations later this decade, will dissect these halos with unprecedented precision, revealing how gas flows in and out of galaxies like cosmic tides. What's emerging is a picture of the circumgalactic medium not as a static boundary, but as a galactic lung breathing in pristine gas from the cosmic web to fuel star formation, while exhaling metal-enriched material blasted out by stellar explosions. This constant exchange could explain why so many baryons seem to vanish from traditional tallies. They're not lost, just cycling through a phase that's incredibly difficult to observe. If that's true, then solving the missing baryon puzzle might require us to rethink where galaxies truly end and where the vast, invisible currents of the cosmos begin. Somewhere between the blazing cores of galaxies and the vast emptiness of cosmic voids lies a realm so sparse it defies conventional detection, the low-density universe. Imagine searching for a single light bulb suspended in a darkened stadium. That's the challenge astronomers face when hunting baryons diffused across millions of light years. This isn't just empty space, it's matter stretched so thin that even the most advanced telescopes struggle to spot it. Yet if simulations are correct, these near-invisible regions could hold the key to balancing the universe's baryon budget. The problem isn't that the matter doesn't exist, it's that it barely interacts with light. In the deepest voids where galaxies are scarce, gas densities might dip below 1 atom per cubic meter. At these extremes, traditional detection methods hit a wall. Optical telescopes see nothing, the gas doesn't glow. X-ray instruments falter. The plasma is too cool to emit high-energy photons. Even ultraviolet absorption studies, so effective for tracing denser filaments, often come up short when probing these desolate stretches. It's like trying to photograph a ghost using a camera designed for daylight. But absence of evidence isn't evidence of absence. Theoretically, this ultra-diffuse gas should still leave subtle imprints on the cosmos. When light from distant quasars traverses these regions, certain wavelengths get weakly absorbed by hydrogen atoms, a phenomenon known as the Lyman alpha forest. Normally, these absorption lines reveal denser gas clouds, but in the void's outskirts, the signal becomes vanishingly faint, smeared across vast distances like ink dissolving in water. Detecting it requires instruments of extraordinary sensitivity, capable of spotting fluctuations in light levels as subtle as 1 part in 100,000. Recent advances are turning the impossible into the merely difficult. The Keck Cosmic Web Imager, with its ability to capture spectra across wide fields of view, has begun teasing out hints of this elusive gas. Meanwhile, the upcoming Extremely Large Telescope and its 39-meter mirror will gather enough light to analyze these whisper-thin absorption features in unprecedented detail. Even more promising are space-based ultraviolet observatories like the proposed LUVOIR mission, which could finally map the low-density universe free from Earth's atmosphere, the cosmic equivalent of switching from candlelight to a spotlight. The real game-changer might lie in combining techniques. Cross-referencing quasar absorption data with weak gravitational lensing maps could reveal where diffuse gas subtly warps spacetime. Pairing X-ray observations with radio surveys might uncover how magnetic fields structure these barren regions. Each approach illuminates a different facet of the problem, like assembling a puzzle where the pieces are made of fog. What makes this clue so tantalizing is its simplicity. The missing baryons might not be hidden in some exotic state or distant corner. They could be everywhere, just spread so thin we've been staring right through them. Solving this piece of the puzzle wouldn't just fill a gap in our cosmic inventory. It would redefine what we consider empty space, revealing a universe far richer and more intricate than we ever imagined. Supermassive black holes aren't just cosmic vacuum cleaners, they're more like chaotic power plants, capable of both devouring matter and flinging it across the universe at nearly the speed of light. While their gravitational pull is strong enough to trap even light itself, their true influence extends far beyond their event horizons. These monsters don't just consume baryons, they transform them, heat them, and sometimes eject them entirely from their host galaxies in spectacular outflows. Could this violent cosmic recycling be hiding a significant portion of the missing baryons? Let's start with the basics. When gas spirals toward a supermassive black hole, it doesn't vanish quietly. Instead, it forms an accretion disk, a swirling maelstrom of plasma heated to millions of degrees, glowing brightly enough to outshine entire galaxies. But not all that material makes it past the point of no return. Magnetic fields and intense radiation can channel some of it into powerful jets, shooting particles hundreds of thousands of light years into intergalactic space. These outflows don't just carry energy, they transport baryons, scattering them far beyond where telescopes can easily detect them. It's like watching a fire hose blast water into a fog bank. The droplets are still there, just spread too thin to see clearly. Then there's the heat. The energy released by active galactic nuclei is so immense that it can ionize surrounding gas, stripping electrons from atoms and rendering the matter virtually invisible to optical telescopes. Entire reservoirs of baryons could be lurking in these superheated halos, too energetic to collapse into stars but too diffused to emit detectable X-rays. Some simulations suggest that over a galaxy's lifetime, its central black hole could eject or ionize enough gas to account for a substantial fraction of its missing baryons, effectively locking them away in a form that's nearly impossible to observe. But here's the twist: black holes might also help reveal where some of the missing baryons are hiding. In galaxy clusters, the superheated gas swirling around active black holes leaves subtle fingerprints in the form of distorted X-ray emissions. By studying these distortions, astronomers can map the otherwise invisible plasma permeating these regions. Observations of the Perseus cluster, for example, show vast ripples in the intracluster medium, evidence of ancient outbursts from its central black hole that pushed baryons into the cluster's outskirts. The real mystery lies in the balance. Do black holes permanently remove baryons from the cosmic ledger, or are they just temporary wastations in a grand cycle of matter? Some theories propose that ejected gas might eventually cool and rain back onto galaxies, replenishing their star-forming fuel. Others suggest that the most energetic outflows could send baryons hurtling into the cosmic web, where they blend into the warm, hot intergalactic medium. The answer might determine whether black holes are cosmic hoarders or inadvertent distributors of the universe's missing matter. New telescopes like the European Space Agency's Athena mission aim to settle the debate by measuring the composition and speed of these outflows with unprecedented precision. Meanwhile, advanced simulations track virtual baryons through the chaotic environment around black holes, offering clues to their ultimate fate. One thing's certain: the universe's most destructive forces might also be its most creative, shaping the distribution of matter on scales we're only beginning to understand. Cosmological simulations paint a breathtakingly detailed picture of the universe's evolution, supercomputer-powered time machines that let us watch billions of years unfold in mere hours. These virtual cosmos obey the same laws of physics as the real one, starting from the Big Bang and growing galaxies, clusters, and filaments just as we observe. Yet there's a glaring discrepancy when it comes to baryons. Simulations consistently show more ordinary matter in certain places than our telescopes can detect. It's as if the universe forgot to follow its own recipe, leaving astrophysicists to wonder: are the simulations wrong, or are we just missing something fundamental about how the real cosmos hides its matter? Take the cosmic web, for example. Simulations like Illustris Tingi or Eagle show vast rivers of gas flowing along dark matter filaments, with baryons piling up at the intersections where galaxy clusters form. When astronomers compare these predictions to observations, the clusters themselves match reasonably well, but the web's finer threads not so much. Simulations suggest filament densities should be 10 to 20 times higher than what we've measured. Somewhere between the virtual and real universe, baryons have gone AWOL. The question is whether they're truly missing or just masquerading as something else. Part of the challenge lies in feedback, the way galaxies and black holes inject energy back into their surroundings. In simulations, even minor tweaks to how supernova or active galactic nuclei eject gas can dramatically change where baryons end up. Too much feedback and virtual galaxies blow away their own gas supplies too early, leaving them starved for star formation. Too little and baryons clump too densely, nothing like the diffuse structures we observe. Getting this balance right is crucial because real galaxies seem to walk a tightrope between holding onto their matter and expelling it entirely. Then there's resolution, the cosmic equivalent of pixel size. Even the best simulations can't track every atom. They approximate gas as fluid parcels thousands of light years across. This means subtle processes like turbulence or magnetic fields shaping gas on small scales might be smoothed over in ways that hide baryons. Imagine trying to predict weather patterns but ignoring individual raindrops. You'd miss how evaporation and condensation subtly redistribute water. Similarly, simulations might overlook micro-scale mechanisms that disperse baryons into hard-to-detect configurations. Observations aren't blameless either. Telescopes have blind spots, especially for the warm-hot intergalactic medium. The gas simulations predict in filaments often emits X-rays too faint for current instruments to catch or absorbs quasar light at wavelengths obscured by Earth's atmosphere. It's like trying to compare a high-resolution painting to a sketch viewed through frosted glass. Until our observational tools match simulations' precision, we can't know for sure where the disconnect lies. What makes this clue so powerful is its two-way street. Discrepancies between simulations and observations don't just highlight missing baryons, they reveal gaps in our understanding of astrophysics itself. Every mismatch is a potential clue pointing to processes we might have underestimated, like cosmic rays accelerating gas out of galaxies or primordial magnetic fields structuring intergalactic plasma. Upcoming simulations, fueled by exascale supercomputers and sharper physical models, aim to close the gap. Meanwhile, next-generation telescopes will test their predictions with unprecedented rigor. The stakes couldn't be higher. If simulations are right, then the universe has hidden half its ordinary matter in plain sight. We just need better tools to see it. If they're wrong, we might be missing a fundamental law governing how matter behaves across cosmic scales. Either way, the answer won't just solve the missing baryon problem. It could redefine our understanding of the universe's architecture. The hunt for the universe's missing baryons is about to get a major upgrade thanks to a new generation of X-ray telescopes poised to revolutionize our view of the cosmos. Right now, we're like detectives squinting through foggy binoculars, catching only fleeting glimpses of the warm-hot intergalactic medium and other elusive baryon hideouts. But with instruments like Athena and Lynx on the horizon, we're trading up to cosmic night vision goggles, capable of spotting even the faintest whispers of matter hiding in the void. Athena, the European Space Agency's flagship X-ray observatory slated for launch in the 2030s, is designed specifically to tackle mysteries like the missing baryons. Its advanced spectrometer can detect the subtle X-ray emissions from million-degree gas with 50 times the sensitivity of current telescopes. That means instead of seeing just the brightest knots of hot plasma in galaxy clusters, Athena could map the faint tendrils connecting them, those very filaments where simulations suggest missing baryons might be pooled. Imagine switching from a flashlight that only illuminates patches of a dark room to one that reveals the entire space in high definition. Suddenly, the shadowy architecture of the cosmic web comes into sharp relief. Then there's Lynx, a proposed NASA mission that takes this even further. With resolution up to 100 times better than Chandra, Lynx wouldn't just spot diffuse gas, it could dissect its structure, measuring how turbulence, magnetic fields, and even galactic winds sculpt these invisible reservoirs. Picture studying a river not just by its surface ripples, but by tracking every current and eddy beneath. For the WHIM, this could be transformative. Right now, we infer its existence mostly through indirect absorption lines in quasar spectra. With Lynx, we might finally see its X-ray glow directly, peering into the vast intergalactic expanses where baryons have long eluded detection. But the real game changer lies in synergy. These telescopes won't work in isolation. They'll combine forces with ultraviolet observatories, radio arrays, and gravitational wave detectors to build a multidimensional map of the universe's hidden matter. Athena's wide-field surveys could identify promising filaments, while Lynx's sharp focus zooms in to analyze their composition. Together, they'd test a daring hypothesis that the missing baryons aren't in some exotic state we've overlooked, but simply spread so thin across cosmic scales that our current tools can't piece them together. The implications stretch far beyond balancing a cosmic ledger. If these telescopes confirm that the WHIM and filamentary gas hold the bulk of missing baryons, it would validate decades of cosmological models while exposing new puzzles. Why does this matter resist clumping into visible structures? How do supernova and black holes redistributed across epochs? The answers could redefine our understanding of galaxy formation, cosmic evolution, and even the fate of the universe itself. What makes this clue so exhilarating is its immediacy. After years of theorizing, we're on the verge of seeing literally where the universe hides its ordinary matter. The same way the Hubble Deep Field transformed our view of galaxies, Athena and Lynx could reveal a hidden layer of reality, teeming with baryons we once thought were lost. And when that curtain lifts, we won't just solve a mystery, we'll witness the cosmos as it truly is in all its intricate, invisible fullness. Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like they're not even there. Billions stream through your body every second without a single interaction, making them nearly impossible to detect, let alone quantify. Yet these shadowy particles might hold a subtle clue to the missing baryon problem, not because they are baryons, but because their behavior could be skewing how we measure ordinary matter in the cosmos. The connection lies in how baryons interact with their environment. When astronomers tally up visible matter in galaxies and clusters, they often rely on indirect methods measuring gravitational effects, analyzing X-ray emissions, or tracking absorption lines in quasar light. But these techniques all depend on one key assumption, that baryons interact with photons or other particles in predictable ways. Enter neutrinos, which don't play by those rules. Their weak interactions mean they seldom leave a mark on the light we use to probe the universe, yet their sheer abundance could subtly alter the dynamics of the gas and plasma we're trying to measure. Take galaxy clusters, for example. These massive structures are often weighed using two methods: gravitational lensing, which measures total mass, including dark matter, and X-ray observations, which track hot gas, aka baryons. The difference between these measurements tells us how much ordinary matter is present. But if neutrinos, which contribute to gravity but not to X-ray emissions, are more prevalent than assumed, they could inflate the lensing signal while leaving the baryon count unchanged. The result, an illusion of missing baryons that aren't actually missing, just masked by neutrino interference. Then there's the cosmic microwave background, our snapshot of the infant universe. Neutrinos from the Big Bang still permeate space today, and their early interactions left faint imprints on this radiation. Cosmologists use these patterns to estimate the universe's total matter content, but neutrino properties aren't fully pinned down. If their masses or abundances differ from current models, it could throw off calculations of how baryons were distributed during cosmic dawn, leading to discrepancies in present-day tallies. The plot thickens when we consider neutrino oscillations, the phenomenon where these particles morph between three distinct types as they travel. This chameleon-like behavior means neutrinos detected near Earth might not represent their original distribution in distant galaxy clusters or filaments. If oscillations are influenced by magnetic fields or matter density in ways we don't yet grasp, they could further obscure the true baryon landscape. Recent experiments like IceCube and SuperCamioc are probing these mysteries, but the answers remain fuzzy. What's clear is that neutrinos, long relegated to the sidelines of the baryon hunt, might be quietly warping the cosmic ledger. Solving this piece of the puzzle won't just help find missing matter, it could redefine our understanding of how invisible particles shape the universe's visible structure. The takeaway: sometimes what's hardest to detect isn't just hidden, it's actively hiding the things we're searching for. And in the case of neutrinos, their ghostly dance through the cosmos might be the reason our baryon accounting still doesn't add up. In the earliest moments of the universe, before stars or galaxies existed, everything came down to numbers, specifically the ratio of baryons to photons. This seemingly simple relationship, frozen into the cosmos just minutes after the Big Bang, holds profound implications for where ordinary matter ended up. The baryon-to-photon ratio tells us how many protons and neutrons existed for every particle of light in that primordial soup. And based on observations of the cosmic microwave background, we've calculated this number with impressive precision, roughly 1 baryon for every 2 billion photons. But here's the catch: when we use this ratio to predict how much ordinary matter the universe should contain today, it doesn't quite match what we actually see. This discrepancy forces astronomers to ask a radical question. What if our understanding of this fundamental ratio is incomplete? The number itself comes from meticulous measurements of the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this ancient light reveal how matter and energy were distributed when the universe was just 380,000 years old. But those measurements assume that all baryons behaved predictably, that none were locked away in some exotic state we haven't accounted for, or that interactions in the early universe didn't skew the ratio in ways our models miss. One possibility lies in the behavior of quarks and gluons before protons and neutrons even formed. In the first microseconds after the Big Bang, matter existed as a seething quark-gluon plasma, a state so extreme it's now recreated in particle colliders like the Large Hadron Collider. Could some baryons have been lost or transformed during this chaotic phase? Some theories propose that temporary imbalances like matter-antimatter asymmetries we don't fully understand might have shifted the final baryon count before the universe cooled enough to lock it in. Then there's the photon side of the equation. Photons aren't just passive markers, their energy influences how matter clumps together. If processes in the early universe, say decaying dark matter particles or primordial black holes, injected extra photons into the cosmic background, it could dilute the apparent baryon-to-photon ratio without actually changing the number of baryons. We'd be measuring a shadow of the true value, like trying to gauge the height of a tree while standing in a funhouse mirror. The stakes are high. If the baryon-to-photon ratio is even slightly different than we think, it would ripple through every calculation of the universe's matter content. Galaxy formation, the growth of cosmic structure, even the eventual fate of the cosmos, all depend on this foundational parameter. Future experiments like next-generation cosmic microwave background surveys or advanced particle colliders could help settle the debate. Either way, revisiting this ratio isn't just about fixing a number. It's about questioning how well we truly understand the universe's first moments and whether we've been missing something fundamental all along. Dark energy and missing baryons seem like unrelated cosmic mysteries. One is the unexplained force accelerating the universe's expansion, the other a shortage of ordinary matter. But could there be a hidden link between them? It's a wild idea, one that borders on cosmic heresy, yet some theorists are starting to wonder, what if dark energy isn't just pushing space apart but subtly rearranging where baryons end up? Consider the timing. Dark energy became dominant around 5 billion years ago, around the same era when galaxies began showing signs of missing baryons. Coincidence? Possibly, but if dark energy's repulsive force does more than just expand space, if it also alters how matter flows on the largest scales, it could explain why baryons seem to have evaporated from our observations. Picture a rising tide not just lifting boats but actively scattering their cargo into deeper waters. The universe's accelerating expansion might be doing something similar, stretching gas filaments so thin they dissolve into near invisibility or pushing baryons into regions where our telescopes can't trace them. Then there's the vacuum itself. Dark energy is often described as a property of empty space, but quantum physics tells us there's no such thing as true emptiness. Even a vacuum teems with particles flickering in and out of existence. Could these quantum fluctuations interact with baryons in ways we don't yet understand? Some speculative models suggest that dark energy might create microscopic pressure gradients, gently herding ordinary matter toward cosmic voids over billions of years. It's a stretch, but not impossible, like a hidden hand tilting the universe's scales. The boldest theories go even further. If dark energy isn't constant but evolves over time, a concept called quintessence, its fluctuations could have periodically heated intergalactic gas, preventing baryons from clumping into detectable structures. Imagine blowing on a foggy window. The moisture doesn't vanish, it just disperses into a finer mist. Similarly, these hypothetical dark energy pulses might have scattered baryons into a state too diffuse for our current tools to spot. Of course, this is all highly speculative. The standard model of cosmology treats dark energy and baryon distribution as separate puzzles, and for good reason. There's no direct evidence linking them. But science thrives on exploring even the unlikeliest connections. After all, history shows us that some of the universe's deepest secrets hide in the gaps between what we think we know. Whether this clue leads anywhere or not, it's a reminder that the cosmos rarely obeys the neat categories we try to impose on it. And sometimes the most outrageous ideas are the ones that crack the case wide open. Between the glittering threads of the cosmic web stretches a realm of nothingness so vast it defies comprehension. The cosmic voids, these sprawling deserts of space, some spanning hundreds of millions of light years, appear eerily empty, devoid of galaxies, stars, or even the faintest wisps of nebulae. But looks can be deceiving. What if these so-called empty regions are actually hiding some of the universe's missing baryons, spread so thin they've escaped detection? The math suggests it's possible. While voids contain far less matter than galaxy clusters or filaments, their sheer volume is staggering. They make up over 80% of the universe's total space. Even a whisper of gas per cubic light-year, when multiplied across these unimaginable expanses, could add up to a significant fraction of the missing baryons. The challenge, finding matter in a near-perfect vacuum, is like trying to weigh a snowflake by watching it fall in a blizzard. Traditional detection methods hit a wall here. The gas in voids isn't just sparse, it's cold, often just a few degrees above absolute zero, making it far too cool to emit detectable X-rays or ultraviolet light. Even the hydrogen that does exist is mostly neutral, meaning it doesn't absorb light from distant quasars as effectively as ionized gas in other regions. It's the cosmic equivalent of trying to spot a single breath of air in an empty stadium. Yet astronomers have their tricks. One approach relies on the Sunyaev-Zeldovich effect, the same distortion in the cosmic microwave background that reveals hot gas in galaxy clusters. In voids, the effect reverses. As microwave photons pass through these colder regions, they lose a tiny bit of energy, creating subtle dips in the background radiation. These shadows hint at the presence of sparse, cool gas that otherwise leaves no trace. Recent surveys like the Atacama Cosmology Telescope have spotted these signatures, suggesting voids might hold more than meets the eye. Another clue comes from the way galaxies move. Even in emptiness, the gravitational tug of unseen matter can subtly alter the trajectories of nearby galaxies. By mapping these peculiar velocities, researchers have found discrepancies void galaxies moving in ways that suggest more mass than visible gas accounts for. It's indirect evidence, like deducing wind patterns from leaves rustling in an otherwise still forest. The most tantalizing possibility: voids might not be as empty as we think. Simulations predict a fog of ultra-diffuse gas lingering in these regions, remnants of matter too far from any galaxy to be pulled into the cosmic web's denser threads. Some theories even suggest that primordial magnetic fields stretched thin over eons could be trapping baryons in these barren expanses, preventing them from clumping into detectable structures. Proving this will require telescopes of unprecedented sensitivity. Upcoming missions like the Square Kilometre Array aim to map hydrogen in the deepest voids using radio waves, while next-generation SIMBI experiments could refine our measurements of those elusive temperature dips. The payoff goes beyond solving a cosmic accounting error. If voids hold even a fraction of the missing baryons, it would mean the universe's empty spaces are quietly hoarding matter in ways we're only beginning to imagine. What makes this clue so profound isn't just the science, it's the irony. The very regions we've long dismissed as cosmic deserts might be hiding the keys to one of astrophysics' greatest puzzles. And if we're right, it would mean that nothingness in the grand scheme of the universe might not be nothing at all. Galaxies aren't static islands of stars, they're more like living ecosystems, constantly breathing baryons in and out across cosmic time. The Baryon cycle describes this dynamic flow of matter, where gas gets pulled into galaxies to form stars, only to be flung back out into the void by supernova or black hole winds. It's a cosmic conveyor belt, and understanding its rhythm could be the key to unlocking where the universe's missing matter has gone. Start with accretion, the process where fresh gas from the cosmic web streams into galaxies, drawn in by gravity's relentless pull. This pristine hydrogen, untouched by stellar furnaces, is the raw fuel for star formation. But not all of it makes it to the galactic core. As the gas spirals inward, it collides with existing material, creating shock waves that heat it to millions of degrees. Some gets trapped in halo-like reservoirs around the galaxy, too energetic to cool and condense into stars but still gravitationally bound. These circumgalactic regions might be hiding a significant stash of baryons, invisible to traditional telescopes but massive enough to tip the cosmic scales. Then there's the explosive phase of the cycle. When massive stars die in supernova, they don't fade quietly. They detonate with enough force to blast surrounding gas clear out of the galaxy. These winds, rich in heavy elements forged in stellar cores, can reach speeds of thousands of kilometers per second, carrying baryons far beyond where they started. Active galactic nuclei, powered by supermassive black holes, amplify this effect. Their jets and radiation inject so much energy into surrounding gas that entire galaxies can be left baryon depleted, their building blocks scattered across intergalactic space like cosmic shrapnel. But here's where it gets interesting. Not all expelled baryons are lost forever. Some models suggest a significant fraction eventually cools and rains back onto the galaxy in a process called recycling. Picture a fountain where water arcs upward before falling back to the basin, except here, the water is ionized plasma and the fountain operates on timescales of billions of years. This returning gas could explain why some galaxies seem to have just enough fuel for ongoing star formation, even after multiple outbursts. The catch: Tracking these returning flows is nearly impossible with current technology. The gas is too diffuse to emit strong X-rays, and its absorption signatures blur into the noise of intergalactic space. The missing baryons might not be missing at all. They could be caught in this vast, slow-motion cycle. Some are riding galactic winds into the cosmic web, others are cooling into invisible halos, and a fraction are even returning to their galactic homes after eons adrift. The challenge is mapping a process that unfolds over epochs far longer than human history. New tools like the James Webb Space Telescope are beginning to trace these flows by studying the chemical fingerprints of gas around distant galaxies, while simulations like Illustris TNG recreate the Baryon cycle in stunning detail, offering testable predictions. What's clear is that galaxies don't hoard matter, they exchange it with the cosmos in a grand, invisible dance. Solving the missing baryon puzzle might mean learning to see this dance in all its complexity, from the fiercest outflows to the faintest returning whispers. And if we succeed, it won't just fill a gap in our cosmic ledger. It will reveal galaxies as dynamic players in the universe's endless story of reinvention. What if the missing baryons aren't hiding at all? What if our entire understanding of gravity is subtly flawed, tricking us into thinking there's matter we can't see when the real issue lies in the equations themselves? That's the radical premise behind modified Newtonian dynamics, a theory that dares to rewrite one of physics' most sacred rules to explain cosmic mysteries without invisible particles. For decades, the leading explanation for galactic rotation curves, how stars orbit a galaxy's center, has been dark matter. The observed speeds don't match predictions based on visible matter alone, suggesting hidden mass must be lending a gravitational hand. But WHIM proposes a different solution. Instead of adding dark matter, what if gravity behaves differently at extremely low accelerations, like those found in galaxies' outer reaches? The math is startlingly simple, a tiny tweak to Newton's second law that perfectly matches galactic rotation without invoking unseen matter. And if WHIM can explain galaxy motions, could it also hold the key to the missing baryon problem? Here's where it gets intriguing. If gravity strengthens slightly more than expected in weak field regimes, it might mean we've overestimated how much ordinary matter the universe needs to create the structures we see. Those missing baryons could simply be an illusion, a misjudgment stemming from flawed gravitational assumptions. Imagine playing a piano tuned slightly sharp. You'd keep searching for missing notes that weren't actually there. WHIM suggests our cosmic ledger might be similarly miscalibrated, yet the theory faces glaring challenges when scaled up. While it excels at galaxy-level predictions, it struggles to explain observations of colliding galaxy clusters like the Bullet Cluster, where gravitational lensing reveals mass clearly separated from visible matter. WHIM proponents have developed relativistic extensions like TVS to address this, but these add complexities that some argue undermine the theory's original elegance. Worse, precise measurements of the cosmic microwave background, the universe's baby picture, align exquisitely with standard cosmology's mix of baryons, dark matter, and dark energy, leaving little room for WHIM alternatives. Perhaps the most fascinating twist comes from recent hybrid approaches. Some theorists explore emergent gravity frameworks where WHIM-like behavior arises from deeper quantum principles, or scenarios where dark matter and modified gravity coexist in unexpected ways. These ideas remain speculative, but they highlight a critical truth. The missing baryon problem might not have a single, tidy solution. Just as quantum mechanics and relativity revolutionized physics by revealing reality's layered complexity, today's cosmological puzzles could demand similarly paradigm-shattering insight. The debate isn't just academic, it cuts to the core of how we understand the universe's scaffolding. If WHIM or its cousins are even partially correct, it would mean that baryons we've long assumed were hidden might be right where they should be, while our theories of gravity are the ones in need of adjustment. Until then, this clue serves as a humbling reminder that sometimes the most profound discoveries begin not with finding answers, but with questioning the questions themselves. The universe doesn't give up its secrets easily, but it does leave clues scattered across every wavelength and particle we can detect. That's why the final piece of the missing Baryon puzzle isn't a single telescope or observation, but a revolutionary way of seeing, the multi-messenger approach. Imagine trying to solve a cosmic jigsaw puzzle while wearing blinders. You'd only ever see a fraction of the picture. For decades, that's how we've hunted for baryons, relying mostly on electromagnetic observations like X-rays, ultraviolet light, and radio waves. But now, by combining gravitational waves, neutrino detections, and traditional astronomy, we're peeling back layers of the universe we've never glimpsed before. Take gravitational waves, the ripples in space-time caused by cataclysmic events like merging black holes. While they don't directly reveal baryons, they're cosmic cartographers pinpointing where massive objects collide and distort the fabric of reality. When LIGO detects a gravitational wave signal from a distant neutron star merger, it gives astronomers a target. Follow-up observations with telescopes like Chandra or Hubble can then search for X-ray or ultraviolet emissions from hot gas stirred up by the collision, gas that might otherwise have gone unnoticed. In 2017, this exact scenario played out when the kilonova event GW170817 flared across the spectrum, revealing heavy elements forged in the merger's aftermath. It was proof that multi-messenger astronomy could illuminate dark corners of the cosmos where baryons might be hiding. Neutrinos add another dimension to this hunt. These ghostly particles, detected by observatories like IceCube, carry information about high-energy processes across the universe. When a neutrino arrives from a particular direction, say near a galaxy cluster, it flags that region as worth scrutinizing. Tracing its path backward might lead us to pockets of hot, diffuse gas too faint to emit detectable light but dense enough to produce neutrino interactions. Some theories even suggest that cosmic neutrinos could be indirectly mapping the distribution of baryons through their travel patterns, like subatomic breadcrumbs leading to hidden reservoirs. The real power emerges when we combine all three. Picture this: a supermassive black hole in a distant galaxy launches a jet of particles at near light speed. Gravitational waves from the black hole's violent activity reveal its location, while neutrinos detected on Earth confirm the jet's existence. Meanwhile, X-ray telescopes measure how the jet heats surrounding gas, and radio arrays track its expansion. Each messenger fills in part of the story, helping us reconstruct not just the event itself, but the baryon-rich environment it's embedded in, gas that might account for some of the universe's missing matter. Collaborative efforts like the Astrophysical Multi-Messenger Observatory Network are already turning this vision into reality. By linking observatories worldwide into a single, rapid response system, scientists can pounce on multi-messenger events within minutes, capturing fleeting signals that might hold clues to baryon distribution. Future projects like the Einstein Telescope for Gravitational Waves or the Pacific Ocean Neutrino Experiment will deepen this synergy, creating a web of observation that spans the entire electromagnetic spectrum and beyond. What makes this clue so transformative isn't just the technology, it's the shift in perspective. For centuries, astronomy meant studying light. Now, we're learning to see the universe through its ripples, its whispers, and its ghostly particles, realizing that the answer to one of cosmology's greatest mysteries might not lie in any single signal, but in the chorus they create together. The missing baryons could be hiding in the gaps between our observations, gaps that only multi-messenger astronomy can fill. So where does this cosmic detective story leave us? After unraveling 25 clues from the ghostly filaments of the cosmic web to the violent outflows of supermassive black holes, we've pieced together a startling realization: the missing baryons aren't truly missing. They're hiding in plain sight, scattered across the universe in forms just beyond the edge of our perception. Some float in the scorching tendrils of the warm, hot intergalactic medium, too diffused to glow. Others lurk in the turbulent halos around galaxies, masked by magnetic fields or lost in the chaos of cosmic collisions. A fraction might even be cycling through the great Baryon fountain, ejected by stellar explosions only to rain back down over eons. Yet despite these breakthroughs, the puzzle isn't fully solved. Every new observation, whether from X-ray telescopes tracing faint plasma or gravitational waves revealing unseen structures, adds another piece to the mosaic. The upcoming Athena mission could finally map the WHIM hidden rivers, while multi-messenger astronomy might expose baryons hiding in the gaps between light and gravity. Even neutrinos, those elusive cosmic phantoms, could be quietly redirecting our search. What's certain is this: the universe never loses matter, it just rearranges it in ways that challenge our imagination. The missing baryon problem isn't a flaw in the cosmos, it's an invitation to look deeper, to question our assumptions, and to embrace the thrill of the unknown. After all, the greatest discoveries often begin with a simple admission: we don't have all the answers yet. So what do you think? Could the solution lie in an overlooked corner of astrophysics, or is there a cosmic twist we haven't even imagined? Drop your wildest theories in the comments, because the next big breakthrough might just start with a spark of curiosity. And who knows, the final clue to this mystery could be hiding in plain sight, waiting for someone like you to connect the dots.